This is a picture of me, complete with my digging equipment and soil sampling and analysis kit, back in the glorious days of summer, standing on top of a superficial clay with flint formation containing clay, silt, sand and gravel, supported by a ports-down chalk formation bedrock. The importance of these terms will become more apparent over the following slides. The underlying geology in this area of Dorset is not only perfect for supporting the location's rich and varied arable farming rotations, but also in providing the local village with a balanced subsoil, which has historically been adopted for the manufacture of earthen mortars for its building stock over many centuries. And so, on with the presentation. My presentation on earthen mortars will be covering the following areas in the context of the United Kingdom and Ireland. A brief history of earthen mortar composition, earthen mortar analysis, subsoil sourcing, subsoil procurement, modifying versus stabilisation, earthen mortars and their future. The Neolithic Revolution signalled a transition from a culture of prehistoric nomadic hunter-gatherer to one of sedentary non-nomadic society. These early forming communities started to focus on localised methods of agriculture, farming, crop and livestock domestication. As local community populations increased, so too did the requirement for permanent settlements which could securely house its inhabitants, livestock and produce. These buildings and structures were constructed using vernacular materials, and so, alongside a variety of other locally sourced available materials, the use of earthen mortars became widely adopted across the United Kingdom and Ireland. Historically, earthen mortars have been adopted within a broad and diverse range of applications. As a daubing material for timber formwork, wattle and daub, mud and stud. As a bedding mortar for brick, terracotta, stone and earthen units. It's been used for pointing, used in flooring, been used as an internal plaster applied to a variety of ceiling and wall substrates, including reed and lath. It's been used as an external render applied across a similar variety of substrates. As a coring material for decorative finishes. Used in small unit construction, for example, earthen bricks and blocks. And it's been used in monolithic walling construction. During the 18th century and later part of the 19th century, transportation and overall national accessibility greatly improved, resulting in an increase in the variety of transportation links and their respective routes throughout the country. The theme of an increasing population continued, and the demand for cheaper, mass-produced and more robust building materials escalated to address developing architectural requirements and the restrictions previously associated with seasonal construction. The rapid development of industry and the continuous kiln met with these rising demands, and a gradual decline in the mainstream traditional use of vernacular materials ensued. Key points. From prehistory, developing communities have shared a close connection with soils and earthen materials for both food and shelter, providing an informative chronology into past civilizations and our shared cultural heritage. Historically, buildings and structures that adopted earthen mortars in their construction relied solely on the local availability of suitable subsoil deposits as a primary source of raw material. On this basis, earthen repair materials should be considered as distinctly unique to geographical location and its underlying geology. The use of earthen mortars can be evidenced by its presence within a variety of both high and low status buildings and structures, and should not be considered as an inferior building material. The recognition of earthen mortars as an inferior material relates largely to the historic changes in societal opinion and a lack due to loss of understanding towards its role and its requirements within the built environment. In the modern context, historic earthen mortars can largely be considered as a concealed material, which are often only revealed as a result of material failure due to inappropriate intervention. The largely underdocumented area of earthen mortars has witnessed a gradual decline in the transference of intergenerational skills and knowledge from the later part of the 19th century. This has contributed to a tangible void in our modern-day understanding, which continues to be to the detriment of our identified and yet to be identified national earthen inventory. So what does an earthen mortar contain? The basic composition of an unstabilized earthen mortar consists of two essential components: the adoption of a subsoil, which contains a well-graded distribution of sand, gravel, silt and clay particles, and a measured addition of water. Although basic in its requisite parts, the wonderful complexity of an earthen mortar should never be underestimated. It should be understood that the inclusion of the terms sand, gravel, silt and clay also relate to a referencing system relating to particle size classification, and as such the reference to sands and gravels encompasses a broad range of mineral groups. Historic earthen mortars are analysed using two approaches. Analysis in the laboratory focuses on the following areas: identifying the mineralogical composition and morphology of an earthen mortar sample and determining the sample's particle size distribution, or PSD. In establishing the mineralogical composition and morphology of an earthen mortar, its chemical compound composition and internal architecture relating to crystalline structure can be revealed. In determining an earth mortar sample's particle size distribution, the sample is disaggregated and passed through a series of sieves of decreasing screen size, with the smaller silt and clay fraction being analysed using a sedigraph. The PSD profile is unique to the earthen mortar and reveals vital information regarding the definition of percentages relating to each particle size classification. The results from these two approaches of analysis identify the unique profile relating to the distinct composition of an applied earthen mortar. These methods are used for both earthen mortar and subsoil analysis. This image demonstrates an example of particle size distribution and reveals the sample's unique particle composition profile. Note that the majority of particles in this example exist within the mid-range, exhibiting a well-graded range of distribution. There is a wealth of information that can be gathered relating to an earthen mortar's characteristic and composition from conducting a series of simple visual, physical and olfactory routines in the field. For visual, observe the interaction of the mortar with partnering materials, including its condition, colour, particle inclusion and texture. For physical, from a small extracted sample, can you dry form the material between your fingers? Introducing a minimal quantity of water, can you form a ball? If you squeeze the formed ball between your fingers and drag the material down your thumb with your finger, does it feel greasy? On parting your fingers, is it sticky? And is it crunchy or paste-like on reforming their connection? On disaggregating the sample on the palm of your hand with a small quantity of water, what mineral particles can you identify? Can you identify an approximate size grading of particles? For olfactory, key information can be gained through smelling an earthen mortar sample. Does the sample smell musty, i.e., could it contain organic material? Can you smell the presence of lime stabilization when the sample has been dampened? Some clay-rich soils smell noticeably more characteristically clayey than clay-lean soils. These methods are used for both earthen mortar and subsoil analysis. Subsoil sourcing can be broken down into two distinct activities. Activity 1 is desk-based and adopts the use of the following resources. The British Geological Survey hosts an interactive online platform which is used in the process of identifying the underlying geology of the project site and potential subsoil extraction sites which match in geological sequence. The platform is also used to reveal additional information relating to environmental designations, for example, SSSI sites, areas of outstanding natural beauty, and conservation areas. Local Ordnance Survey maps provide an invaluable resource for identifying the location of potential historical extraction sites and in providing additional localized contextual information. Google satellite view maps assist in walking potential extraction sites virtually to reveal a site's topography and any associated considerations towards access and risk. Activity 2 is field-based and consists of conducting the following activities. Field-based investigation is informed by the preceding desk-based research and requires a permission to dig from the landowner. After digging a number of strategically positioned trial pits, sample should be extracted from a series of defined depths for the purpose of both off-site laboratory and on-site field analysis. It is useful to establish the consistency relating to the stability of a subsoil's composition in each trial pit across the site. All subsoil samples will be analysed against the earthen mortar until a profile match can be confirmed. So what does a subsoil look like? Subsoils provide us with the raw material used in the manufacture of earthen mortars, and as such it is vital to accurately identify this section within the soil. The image illustrates a trial pit dug in the field of a small village in North Dorset. Note its tonally distinctive layers. Note the top layer of green vegetation. The topsoil stratum is the darker organic layer, and the subsoil stratum, which is indicated by the creamy white area toward the bottom of the image. In this example, the subsoil predominantly consists of chalk encased within a gravel, sand, silt, clay. The top of the subsoil range can normally be revealed at 450 millimeters, of which the layer's depth varies across the centre of the village. To the left boundary of the village, the subsoil is of head, which is a poorly sorted and stratified angular rock with gravel, sand, silt and clay particles, and to the right boundary of the village exists a subsoil of alluvium, which is an unconsolidated gravel, sand, silt and clay. This variation exists across a distance of less than 1 mile. It is useful to remember that earthen repair materials should be considered as distinctly unique to geographical location and its underlying geology. This slide illustrates a comparison of 2 subsoil samples which have been adopted in the manufacture of an earthen mortar. Both samples are, however, characteristically very different. Sample A is from South Wales and has been adopted as a bedding mortar. The subsoil composition comprises of a brown and red fine to coarse grained quartzitic sandstone with subordinate mudstones and sparse limestones. The clay particle fraction is between 16 to 18%. Sample B is from Wiltshire and has been adopted as an earth render. The subsoil composition comprises of chalk with angular and rounded flints within a sandy clay. The clay particle fraction is between 23 to 28%. Based on the results of analysis, each subsoil sample profile confirms a match in the composition of its respective historic earthen mortar. On establishing a number of suitable source locations for the subsoil, the process of material negotiation and procurement commences. This involves careful planning and consideration and can often be dependent on environmental and seasonal restrictions. There are many factors that affect the success of procurement, and as such, a short, non-exhaustive list of high-level points have been included. It should be noted that this list is not formatted in any particular sequence. However, it does provide a stable starting point to encourage further discussion. As intimated in previous slides, subsoils for earthen mortars are not a generic off-the-shelf product, nor should they be considered as one. The common misconception is that raw materials can simply be procured in a ready-to-use pre-refined state in the same manner that lime mortars can be procured from a variety of regional manufacturers. This ill perception is fundamentally detrimental to a project. Based on the underlying processes related to earthen mortar analysis, sourcing and procurement, it is of great importance to embark on all 3 of these discussed areas at the earliest possible stages of a project. A further consideration relates to earth modification or stabilization. There are 2 ranges of modification: modifying with additional sand or gravel particles to create a well-graded and balanced earthen mortar if the subsoil is considered too clay-rich for a specific application and therefore prone to excessive shrinkage and cracking, and modifying with additional clay if the binder fraction in the subsoil requires increasing for a specific application to reduce a poorly cohesive subsoil with limited forming and bonding characteristics. Before considering stabilizing an earthen mortar with lime, carefully consider the basis for its inclusion. Is it justified? What is trying to be achieved? And is this contextually relevant and indeed authentic in relation to the applied historic earthen mortar? It should be noted that if stabilization should be considered, that all subsoils respond differently to its addition, and as such, a detailed study of trials should first be conducted and documented. There is currently a tangible information and skills void which threatens the future integrity of historic earthen architecture. Raising awareness and understanding toward earthen mortars is vital in developing and promoting best practice and sustainable approaches toward their long-term conservation. There needs to be greater commitment to actively seek opportunities to increase the upskilling of both conservation professionals and property owners to assist in broadening confidence toward making well-informed interventions based on best practice. There needs to be greater commitment to raise the profile of earthen mortars to increase subject exposure in the context of heritage conservation and disseminate information based on an engaged platform of coordinated research. The subject of earthen mortars in the aforementioned context remains largely underrepresented and certainly underdocumented. The commissioning of case studies and a structured methodology of recording is of vital importance in providing a stable future reference to support earthen conservation.